Afternoon, everyone. So myself Shilpa Rudravar, and today I will be discussing you about CMOS combination logic. So without wasting time, I'm just going towards the CMOS combination logic. We were started with this logic in the last lecture. So just I want to remind you or recall the concept. So here we are designing combination logic using CMOS, that is pull up and pull down network, NMOS on PMOS, because CMOS is the complementary MOSFET, which is the combination of PMOS in pull-up network and NMOS in pull-down network. And secondly, you'll able to explain whatever the logic you have implemented using PMOS or CMOS. Sorry. So this we have already done 2 times. So I'm not going in detail. Always PMOS should be connected in pull-up network as it passes strong 1, and NMOS should be connected in pull-down network as it passes strong 0. And justification of this is given in the previous lecture. Always whenever you are arranging CMOS, that is PMOS and NMOS, only one device or one circuitry, pull-up circuitry or pull-down circuitry will be on at a time, and that's why there will not be direct connection of VDD to VSS, and that's why power consumption is less in CMOS. So next, these are the pros and cons already done. Now this is the main and important thing, and this thing you need to note down. So simplification of this I have written over here. So what is the meaning of this? So whenever you need to implement any combination logic using CMOS, as you know, there are PMOS and NMOS devices. Depending upon how many variable combination logic you need to implement, NMOS and PMOS should be in the proper connection, whether it is series, parallel, mix, like this. Okay. The complementary CMOS is the inverting logic, so as to implement only functions such as NAND, NOR, and XOR. These are the complementary, means invert logic. And if I need to implement AND gate instead of NAND gate, I need to implement it by using inverter in front of that. So I am able to implement inverted logic in CMOS. I can implement non-inverting logic also, but more circuitry I need to add. So inverter I need to add in front of that. So hope that point will be covered in the coming PPT. So here, what is the meaning of this? As you know, the pull-up network PMOS are connected, and pull-down network NMOS are connected. So whenever the equation, in the equation you are getting A into B. In the equation, if the term is coming like A multiplied with B, so you need to implement NMOS in such a way that 2 transistors will be in series. So here this is the NMOS, and if A into B combination you need to implement, so it's 2 NMOS, as there are 2 variable A and B which are in multiplication A into B fashion. So you need to connect that 2 transistor in series, and just keep the note of that N transistor is not having bubble. So symbols of this NMOS and PMOS you need to understand. Keep a note of that. Then whenever you need to implement A plus B like combination in NMOS, so you need to connect that 2 in parallel. So parallel, there is one transistor and there is another transistor. The facing of the transistor might be in front of each other or like this. So there is no such a thing like you need to draw like this only. Okay. So for NMOS, A into B, that will be in series, and A plus B, that will be in parallel. And for PMOS, you need to do the opposite thing, that for A plus B you need to make PMOS in series, and for A into B you need to make PMOS in parallel. So it is my request that for understanding purpose and remembering purpose, only remember one part, that is NMOS. If A into B is series, A plus B is parallel. Just do the opposite of that. If you are trying to remember both the things at the same time, it will create a confusion. Okay, so this bubble is for the PMOS. So hope these things are clear to you. And as we are having CMOS connection, CMOS implementation, so we required double transistor, that is number of PMOS equal to the number of NMOS. So 2 PMOS means 2 NMOS. So total you require 4 transistors. So that number of transistors increases for the CMOS logic. So this up to this we have covered in the previous lecture. Now, whenever you need to implement inverter, as you know, first step is that you need to write its equation. So I'm writing Q equal to A complement. A dash is nothing but A complement. So instead of writing that bar, I have written dash. Okay, so I am having how many variables? Only one variable. And what is the output? That is only a one variable. So I require one PMOS and one NMOS. Now, as you know, previously I have already taken that PMOS should be connected in pull-up network and NMOS should be connected in pull-down network. So PMOS is taken and this NMOS is taken, which is placed at its own position. And intersection of this point is called as a Q, and two inputs are combined together to form your one input of NOT gate. So this is one A. Now all the things are very important. If you are not giving VDD, circuit will not be complete. If you are not giving VSS, circuit will not be complete. So everything, every notation is very important. So VDD, VSS, input, output, you need to specify properly. So here, this is your what inverter. Now one thing is missing over there. I already told you that you need to draw or write notation, which is source and which is drain, which is gate, so that it will be easy for you to understand. So here always I told you for the P transistor, source will be this. So always for P transistor, this is what is the this is what is the source, and this is drain. Okay, this is gate. Again for N transistor, this is gate and this is drain and this is source. So opposite of that of PMOS. So always remember this. If I am putting NMOS in the for certain purpose, if I am putting NMOS towards VDD, so that should be drain. Drain should be connected to VDD. It will never happen in the combination circuit that you need to connect NMOS in the pull-up network. But just for having knowledge of that, I'm just telling always for PMOS, source should be connected to VDD. Drain at the downside, both the drains are connected together. PMOS and NMOS drain are connected together to form the Q, that is the output, and source of the NMOS is connected to ground, and gate of these two are connected together to form single input. So hope these things are clear. Now I told you how this is working. Suppose my input to this transistor or this circuit, NOT gate, is 1. Because I need to prove it. Only by drawing the circuitry is not sufficient. You need to justify that whatever implemented circuits is behaving as a NOT gate or not. So if I am giving input as a 1, what will happen? As I told you, and you need to remember this point also and write down in your notebook that PMOS is an active low device. What? PMOS is an active low device because bubble is present. Active low means this device will turn on when 0 is applied. And this is active high device means when 1 is applied, this device will be acting as a switch, on switch. So as already I told you, always we are using transistor over here are the enhancement type of PMOS and NMOS. Secondly, these transistors are working as a switch only, whether the switch is on or off. That's why that will be working in the cutoff state and the saturation region only. Okay. So that already I have cleared so many times. So I'm not going in the detail of that. So when 1 is applied, what will happen? This transistor will be on and at the same time this will be off. Okay. And as this is on, what will happen? This particular VSS is connected to the output and that's why output will be 0. Okay. Now when I am giving 0 as an input to the both the devices, what will happen? When I am giving 0 as an input, as this is the active low device, it will turn on. At the same time, this will turn off. Now, which path you are getting at the output? You are getting this VDD to output path, and that's why output will be 1. So from this, we can prove that when 1 is given, output is 0, and when 0 is given, output is 1, means it is inverting the logic. So hope this point is clear to you. So I'm going towards the next point. Okay. So next PPT over here. Now you need to implement. Now keep your notebook with you and pencil pen with you. So you need to implement NAND gate. Why I have taken NAND gate first, not AND gate? Because whenever you are implementing any circuit using CMOS, it implements inverted logic. Okay. So what is meant by that inverted logic? If I have written here, it is written as a into B complement. Now you should know the things properly. Implement this NAND gate. So NAND gate is defined by this equation. So first step is to write equation if that is not given. So here equation is A into B whole complement. Now you know that A complement into B complement is totally different from A into B whole complement. That De Morgan's theorem, just remember. So here A into B whole complement is given. Okay. So now this AND gate is defined as like this gate. This is the AND gate. When inputs are two inputs, I am considering here two input NAND gate. So my output is Y equal to AB whole bar. Now, as you know, this thing is very important. Now I need to implement pull-up network and pull-down network. So this part is the pull-up network. As you are able to see, this particular part is the pull-up network part, because here PMOS are connected, and this part is the pull-down network, that is NMOS are connected. Okay, so first it is my habit to first draw NMOS. Depending upon your convenience, you can draw NMOS or PMOS first. So why I am drawing NMOS first? Because this A into B is they are considered as a series connection of NMOS. So this is directly proportional. So we are considering A into B, that is series, A plus B, that is parallel. So that come in my mind like that. So I always draw NMOS first. So what is the role? I am having this A into B. Just don't see this complement at this moment. So A into B. What is the meaning of A into B for NMOS? They are in series. So here there is first NMOS which is drawn, and second NMOS is drawn. Now I need to connect that into series. So I have connected these 2 points with each other. Okay. Now again here I have not mentioned source and drain, but you in your notebook you need to write proper source drain connection. So for NMOS, as I told you, this is drain, this is source, again this is drain, again this is source, and these are gates. Hope these things are clear to you. Again, for your convenience, I'm just writing always for NMOS, this is drain, this is source, again this is what? Drain, and this is source. Okay, is it clear? This is gate and this is again another gate. So as I'm having two variables, so I have drawn here two NMOS, and as in equation it is given A into B. So meaning of A into B is that NMOS should be connected in series. That's why NMOS are connected in series. Hope this thing is clear in pull down network. Now what you need to do, just opposite of this, you need to go for the PMOS. As you need it is written over here A into B. What is meaning of that? That parallel connection of PMOS. So you need require two PMOS, as there are two variables A and B. So this is my first PMOS and this is my second PMOS, and you need to connect it parallelly. Now how to connect it? Suppose this is the PMOS. Just bear with the drawing, because I'm not able to draw it properly, but still I'm trying to draw. So always if you are drawing like this PMOS, this is totally wrong. Why it is totally wrong? Because you need to draw this bubble. This is very important, otherwise your symbol is a symbol of NMOSFET, and many of the students are doing this mistake every time. So this is the thing. So instead of drawing like this, you can draw like this in front of each other, and parallel means one parallel with other. Again this parallel with this. Likewise you can draw the circuitry, and here always PMOS should be connected in pull up network, so it should be connected to VDD. So all these notations are very, very important. And what is this? This terminal is source. As I told you, for the PMOS it is source. So this is also source. This is gate. So this is also gate, and this is drain. Both are drain. So drain are connected together. So here is drain and here is drain. Hope the drawing is clear with you. So I'm not going fast, I think. So same way you need to draw in your notebook. So parallel means like this and series means like this. So as there is in pull up and pull down network, it is shown that intersection of pull up and pull down forms your output. So this is the intersection of pull up and pull down, and from this you have taken the output, and here properly write what type of output you are getting. As you are implemented for NAND gate, so you need to write Y equal to A into B complement. So what is remaining over here? I told you these notations are not given, so you need to give the notation. Now I have drawn this diagram. Everything is over because I am having into A into B only. This is the equation. So A into B is implemented in NMOS as a series combination and implemented in PMOS as a parallel combination. Intersection of that is forming your output, and A should be connected with A because there are two transistors. One is for A variable, another is for B variable. So A with A and B with B you need to connect. Okay, otherwise you need to give different input, and this should not happen as there are the only two inputs. So you need to combine that with each other. So Now you have designed this circuitry, but now after designing, whether you have implemented this circuitry properly or not, whether it is giving output properly or not, how to check it? So it has been checked using this particular table. Now how many inputs you are having? Hope everyone getting the things properly. I am able to see some question on the question box. So not audible. Okay, that is previous. So hope this point is clear up to this, because on this basis only you need to implement each and every circuitry. So learning by doing is the best option you are having with you. So pen paper should be with you if you are not taken. So how many inputs you are having? So I am having two inputs. So I have written A and B, which are the two inputs. Now, as there are two inputs, how many combinations are possible? So there are four combinations possible. That is 0, 0, 0, 1, 1, 0, and 1, 1. So I have written this as a truth table. Same way you have written. Now, always you need to give numbering to the transistor. So which transistor is T1, T2? So you can give these as a T1, T2 likewise, but whatever you are giving, just stick to that. So I have given T1 as this, T2 as this, T3 and T4. So I can say this T1 and T2 are what? PMOS. So I'm writing this as a PMOS transistor for your understanding over here. And these are my NMOS transistor because it is shown over here. So these are my NMOS transistor. Now you need to write at what point this transistor are turning on so that I can trace the path for the output. Now, as you know, this transistor are acting as a switch. Okay, so the transistor will be on or off. There will not be another condition other than this. So now, first option I am taking, that is 0, 0. Hope you are with me and writing properly, because this is very important. So I am giving input A as a 0 and input B as a 0. I am writing over here. Okay. Now as A is given over here and it is applied to this T1. So it is an active low device and that's why this will turn on. So I am just tick marking over here so that it means that it is on. So here it is written as on. Now this A is again applied to this T3, but this is the NMOS and it turns on when 1 is applied. So at this moment, this device is off. Is it clear to you? Now, when B is 0, what is happening? This B is applied to this T2 transistor and that's why this T2 will be on. But same time that B is applied to this T4 and this T4 will be what? It will be in the off state. So now, as I told you, as CMOS circuitry, only one network will be on at a time. It never happens that both the networks are on. So here you are able to see only this PMOS network is on, as it is having path from this to this also, or path like this to this from from VDD to output. So I am getting path like this to this. So this path is off, means this VSS is not connected to output, and that's why what will happen at the output I will be getting VDD. So here it is mentioned that output is 1. Hope the things are clear. So here I am giving that when 0 and 1 is applied. So here is the circuitry and I am applying, I am going fast. So I need to apply A as a 0 and B as a 1. So this is mentioned over here. So this option I am giving. Now I need to see whether which device is on and which device is off. So here, as you know, so 0 is applied to what? 0 is applied to this device and this 0 is applied to this device. Now just check. This T1 is the transistor, PMOS transistor. When 0 is applied, what will happen? That transistor T1 will be on. So here it is mentioned that transistor T1 is on. So here I am writing on. Now when 0 is applied to T3, what will happen? This will be in the off state because NMOS required logic 1 to turn on, and that's why this T3 will be in the off state. Okay, this way you need to go. Now next time, whenever I am giving logic 1, what will happen? This logic 1 is applied to this particular transistor as well as this transistor. So this transistor is what? T2, which is PMOS, and PMOS requires 0 to turn on. That's why this will be off. Okay, as this is off and 1 is applied to this NMOS, so this NMOS will be on. Now just see the connection. This VDD is connected to this output from this side because there are two paths available. One is off, but still another is on. And if I want to see this path, this is on, but as these are the series connection, there is a gap between this, means this is not on, and that's why this ground will not be connected to the output, and your path of output will be like this. VDD will be connected to output, and that's why my output is what? 1. So again we have proved that this particular part. Okay, same way you need to see for this. I am going in quick way to elaborate this, because from next lecture onward, I'm sorry, next equation onward, I'm not going to elaborate this thing again. So what is my third condition? Third condition is that A is 0 and B is, sorry, A is 1 and B is 0. So first you need to give it by pencil. If you are having pencil, just put the thing, because every time you need to rub for the each and every option. So my input is, this is 1 and this is 0. So like this. So this is 1 and this is 0. So this 1 is applied to what? This and this transistor. So as 1 is applied to this transistor will be off, as this is the PMOS transistor, and this transistor will be on. Same way, if I need to check if 0 is applied, so this 0 is applied to which transistor? This transistor as well as this transistor. And as 0 is applied to PMOS, PMOS turns on 0, that's why this will be on. And this transistor is NMOS, which will turn off on the application of 0. Again, you are able to see this is not continuous path, because there is a break. One device is on, another is off. But here you are able to see, as there are two paths available, from one path you are able to connect your output, and that's why I can say VDD is connected to output. And here I have proved that one is at the output you are getting. Now for the last option we are having. So what is the last option? That is, I have to give 1 and 1. So here in last option I have given 1 1. Now as you know, PMOS turns on when 1 is applied and turns off when 1 is applied, and that's why here it is mentioned that PMOS are off, because I told you these are the PMOS and these are the NMOS. So as you know, without going to the diagram also, you can see 1 1 PMOS will be off and NMOS will be on. As NMOS are on, means these two transistors are on and these two transistors are off, what will happen? Direct path to the output you are getting like this, and that's why this VSS is connected to output. VSS means 0, and that's why your output is 0. So hope the things are clear with you. In this way you need to draw the truth table. It is only possible for 3 variable maximum, because if variable increases, that is A, B, C, D, so there will be 16 options, so that will be hectic for you. So only up to 2 or 3, maximum 2. I think 2 is okay. So you can just try yourself to understand in the better way. Hope these things are clear. So I am going in the next PPT. So here, so this is what is the NAND gate. Now if you want to implement AND gate, it should not be like that key I am able to implement only NAND gate. There should be condition that I should able to implement AND gate also. So how to implement AND gate? As you know, AND gate is what? If I am implementing NAND gate and if in between, in front of that, if I am connecting one inverter, this will be acting as my AND gate, because the A bar be over here. So at output it will be A double bar, bar will get cancelled. So I will be getting AB. So in this way I will be getting AND gate. So what I need to do? I need to draw this diagram, and in front of that I need to connect one inverter. Which type of inverter? That to CMOS inverter. You can't draw like this inverter, because everything we are implementing in the form of CMOS. So this thing I am sharing with you. So here, this is the circuit. Are you able to see? So here we have implemented AND logic. So how to implement AND logic? NAND logic, which you implement directly using CMOS, and in front of that if you are putting one NOT gate means this is the NOT gate. Proper notations you need to give. As I told you, this is the source, drain, gate, again drain, source, likewise every time you need to give notation. So what will be the difference in this truth table? So up to this point your truth table is the same. So up to this point my truth table is same. Okay, what you need to do, instead of this I need to again add this two transistor where I have not added over here. So what are the transistor name? I can give here. My transistor is T5 and this is T6. Okay, so you can add two columns over here, T5 and T6. Now as this particular condition is happening, that 0 you are getting, so 0 if you are getting over here 0 0, for that you will be getting certain output. Suppose for 0 0 NAND gate you are getting 1. So when 1 is given, what will happen? This transistor will be in off state and this transistor will be on state. So you need to write in front of that T5 is off and T6 is on. And as this is on, what will happen? Output is connected to ground, and that's why my output is 0 here. Same way, second time also you are getting 1, so your output will be 0. Third time you are also getting 1, so output is 0. And last time, whenever both the inputs are 1 1 over here, output of NAND gate will be 0. And as inverter is connected, 0 is given to the PMOS, so PMOS will be on and NMOS will be off, and that's why VDD will be connected to output. And in this way I am getting the truth table of AND gate, means I have verified this logic is working properly. Hope the things are clear with you. So I am moving forward. So how to implement inverted logic as well as non-inverted logic, I already told you. Same way you need to implement in your book any equation, just take it and try to implement. So I'm moving forward. So what is this? This is the NOR gate. What will be the NOR gate? NOR gate is totally opposite that of the NAND gate. So in NAND gate, we are having NMOS in series. So here PMOS will be in series and NMOS will be in parallel. Why? Because whenever the A plus B you need to implement in NMOS using for NMOS, so A plus B will be implemented as a what? Parallel logic. So you need to have both A and B transistor in parallel, and opposite of that for the PMOS, so it will be in series. So hope these things are clear. Again, same manner, as I have verified the truth table, same way you need to verify the truth table. So as you know, in the NOR gate, what will happen? It is opposite to OR. So this is the truth table of your OR gate, NOR gate. So hope these things are clear. I am not going in detail because I have explained in detail related to NAND gate. So opposite to that, it is the NOR gate. So just PMOS previously are connected in the series, are connected over here in parallel, and opposite to that, they are connected in series. That is PMOS are in series. As this is the two variable, that's why you require two PMOS and two NMOS. What is the missing over here? As I told you earlier, that notations I have not given, that is source, drain, gate, source, drain, gate, drain, gate. Then this is drain, so this is the NMOS, so this is D, this is D, this is S, and this is gate. So likewise, every time you need to apply this VDD, ground, A, B, T1, T2, source, drain, and this output. This is very important, otherwise marks will get deducted. So hope these things are clear with you. So I have explained what NOR gate. Now if you need to implement 3 variable, 4 variable, you can implement easily. Instead of here, if I told you to implement 3 variable NOR gates, what you need to do? Instead of this 2 transistor in series, you need to connect 3 transistor in series and 3 NMOS transistor in parallel. So that is the thing. So in microwave practical, whatever you need to perform the practical related to VLSI, you need to implement inverter, second 3 variable AND gate, 3 variable NAND gate. Sorry, 3 variable NAND gate and 3 variable NOR gate you need to implement. So just draw by your own on the paper that 3 variable NAND and NOR gate. It will be easy for you to implement using microwave. How to implement using microwave, I will tell you afterward, because in this session it is not related to practical. So I am launching the poll. So PMOS logic, series implement and which gate, and parallel implements which gate? B. So this is the right answer, as I told you in earlier PPTs also. Next poll question I am launching, just opposite to that. So here, now there should not be to that. So NMOS series connection means A dot B. So what is the answer? NMOS. A into B implement AND gate, that is series, and A plus B, that is parallel. So A plus B is the OR and A into B is the AND. So my answer is A. So hope these things are clear to you. Those who have given wrong answer, just think upon that and clear that thing in your mind. So I'm hiding. Third poll question, that is, I already told you. How many of you recall the things? Just check. CMOS logic is inverting logic. Do it fast. What is mean by inverting logic? CMOS means PMOS and NMOS, and PMOS should be connected in pull-up network and NMOS should be connected in pull-down network. Suppose I am having one PMOS and one NMOS. I have connected PMOS in pull-up network and connected NMOS in pull-down network. So which logic you are able to implement? That is, we have taken it earlier. Sharing the result. Why I am sharing? It is not to show that how many students have given wrong answer, but this should not happen. You should get the idea that how many students are giving wrong answer, and that wrong answer is not proper. So you need to think on before giving the answer. Okay, so CMOS logic is inverting logic, because whenever I am putting PMOS in the pull-up network and NMOS in the pull-down network, it implements inverter. And as I told you, directly CMOS logic implements inverted logic. So we have taken directly NAND gate first, and after that we have taken AND gate, so that in front of NAND gate I can connect one inverter, CMOS inverter, to make it AND gate. Okay, so hope the things are clear. So what is the answer to this? It is true. Logic CMOS is a inverting logic. Okay, so those who have given wrong answer, just keep a note of that. So now one thing, now I told you in one way that if something in series, so you need to connect NMOS in series. If A plus B, NMOS should be connected in parallel. Now can you see this diagram and can you identify reverse engineering? Just do reverse engineering, and can you identify what equation it is implementing? Just see, NMOS, these are in parallel. Parallel combination is coming in series with another parallel combination. So just try to write down which type of logic the circuit is. A, B parallel. So what is meant by A, B parallel? NMOS in parallel. For which type of combination? A plus B. These are parallel. C plus D. These are series. So A plus B in series with C plus D. I'm mentioning over here for understanding purpose. Some question I'm able to see. Okay. So here NMOS, whenever A into B, they are in series. So here what are the condition? A parallel with B. So parallel means my equation for this is what? A plus B. Now same is happening over here. So my equation for this is C plus D. But both are in series. So series means into. So A plus B into C plus D. That is the equation. And complement you are getting. So always your circuit is having inverted logic. So I am going to this particular point if you are not understood. So this is the okay. So hope you are able to see. So this logic, whatever implemented, is A plus B into C plus D whole complement. Why whole complement? As I told you, whenever you are implementing any circuit using CMOS, it is implemented as an inverted logic. So here A plus B. What is meant by A plus B? Just see. First, I am able to see this NMOS. So what is this NMOS? These are parallel, because A plus B implements parallel and NMOS. So I will be drawing two parallel NMOS. So this is my first NMOS and this is my second NMOS. These are in parallel. Why these are in parallel? Because in equation it is mentioned that this is what is A plus B. So here is the B. Hope you are writing with me. So next, series. What is mean by series? That is dot indicate series for NMOS. So series is indicated by this line. Again, what is the meaning of this C plus D? C plus D means parallel combination of NMOS. So again, I am drawing two NMOS in parallel. So this is the first NMOS. What is the name of that NMOS? That is, here it is mentioned as a C. So whatever the naming is given, same name you need to give. Don't give small letters. If the capital naming is there, it matters a lot. So likewise, this is what we have connected this two transistor in parallel. Now CD. At the same time, you need to give notation, otherwise you will be in the confusion state whether to give C, D, A, B. So this way you are implemented, means what is the meaning of that? A plus B, that is parallel combination of NMOS, and this is the parallel combination NMOS, are in series. So this is one parallel combination, another parallel combination, they are connected in series because of this dot. Okay. Opposite of that you need to do for the PMOS. So what is the opposite to this? That is, these two are in parallel, so this will come in series. So here we have drawn PMOS, bubble is shown, that is the PMOS. So PMOS connected in series. Again, this series you need to convert it into opposite, means parallel. So parallel means like this. Always consider in this way that series means vertical line and parallel means horizontal line. Okay, likewise also you can consider. So as this is series, in PMOS it will be parallel. So I am drawing this line. Now what I need to implement? Again I need to implement this C parallel with D. So what is that? C parallel with D in PMOS will be C in series with D. So likewise this structure will be there. So here these two parallel combination were in series. Now in PMOS these two series combination will be in parallel. So in this way, intersection of these two pull up and pull down network, you are getting the output, and output is A plus B into C plus D whole complement. Okay, because it is implementing inverting logic, that's why it is complement is mentioned over here. So hope the things are clear with you. If not, just do the practice of that, because until unless you are not doing the practice, it is difficult to understand. Okay, so anybody having any problem? Are you doing by parallel with me on pen and paper? So hope the things are clear. Okay, so this way every time this table is very important to understand. So in this way we have implemented the combination logic A plus B into C plus D whole bar. Now moving towards the next logic. Now here, how this logic is different from previous logic whatever we have seen. Now here complement is not present, and as I told you earlier, whatever logic implemented using CMOS is implemented as a complemented logic, but now here complement is not present. So what to do in such case? What to do in such case? That as I want to implement CMOS circuit, meaning of that it is a complemented logic. So I need to rewrite this equation in such a way that it will give complemented structure. So I want my structure to be like this, complement. Now I can't put complement over here like this. Why? Because if I'm putting like this will the total different logic. So to avoid that, what I'm doing, I am just taking two signs, complement. I mean complement and complement will cancel each other. Understood? First step, what? That in previous PPTs or previous examples, we had a complemented logic, but here we don't have complemented logic. So what you need to do? We need to write this equation in terms of complemented logic. So to write the equation in terms of complemented, right, it is not possible to only draw one line, because it will change your logic. So what you need to do, whenever you are doing complement, two times complement means these are cancelling each other, means nothing but whatever equation you are having previously will be like that only. So I have written over here what? Two lines. Means complement will be cancel each other, means it is nothing but your original equation only, just we have written in the different way. Now for this, solving this equation, you should know De Morgan's theorem. What is De Morgan's theorem and how to statement it? So complement, first start with this complement of product. किसका complement है? Product का. So complement of product is equal to sum of complements. Sum of complements. These are the different. Here it is complement of A into B, but here it is the addition of complements. So this you should know, then and only then you will able to solve this. And this is basic thing which is covered in the first year, second year. So second, how to read? Complement of sum is equal to product of complement. Just if you are not knowing, just write down in your notebook in the way I am telling. So what you need to write? First consider this complement. So complement of what? Product is equal to what? Sum of complements. Then complement of sum is equal to product of complement. Okay, this is the very important. Now I have written this in the different way by giving two complements. So complement will cancel each other, but what we need to do now, we require the diagram like this, or equation is like this. So we require equation like this. So I need to resolve this particular equation. So how to resolve? So I have taken that in this format. So what I have taken? So I have taken like this. Okay, what is the meaning of this? I have solved this particular part. Which part? I have solved this particular part. How to solve? Using this De Morgan theorem. So now complement is present over here. Now complement of sum, because these are the total individual product and this is individual product, but this is the addition. So complement of sum is what? Product of complement, and that's why I have written product of complement over here. So this is, instead of plus, there will be into, and a bar will get cancelled, and b bar will be there. So a plus b, because this is what? A into B will go into A plus B, because this complement you need to solve. So after solving, you are getting this particular part. If you are not clear about this particular logic, just recall your concept, learn the De Morgan's theorem and try to learn it. So after this, what I need to do? I need not have to remove this
Hello.
Complement.
Madam.
Hello.
Madam, we have to end up.
Okay.
Sorry,
okay. Okay. We are going out of time, so time is running. So I will stop over here. Just try to implement or try to solve this equation that as I have solved up to this, so that it will be easy to implement using CMOS. Okay, so I am